Okay everyone, we're going to finish off the area under curves today, and today we're going to get the exact areas. How exciting! Okay, so we're going to talk again about our little rectangles. Let's do that right now. And yes, we're going to be looking at limits again. Back to the Riemann sums, and we're going to look at a limit. So a question for you. If you wanted to know the area under this curve, let's just say the blue area, the area that's designated A here, how could you do that? Well, we already talked about our trapezoids, but let's go back to our rectangles. You could make some rectangles, right? I could put one rectangle here. This is right bound. I could put another one of the same width, which I guess would go to about here. And maybe another one. I know I didn't work it out perfectly, but let's say another one here. So we got three. They're supposed to be the same width. All right, well, we could do that. Is that going to be the most accurate? No. So my question for you is, if I wanted to use rectangles to approximate the area under a curve, how many rectangles would be best to use to be as accurate as possible? Like, don't use 3. What would you do? You'd use more than 3. A lot more than 3. Like how many? Like, how about as many as possible? That would be really great. In fact, you would want to do infinite number if you could. Now, I know before calculus you couldn't really do stuff like infinite, but with calculus, we've done it before, we're going to do it again. We're going to put infinite rectangles. Now, I'm not going to draw them all, but this is the idea. You're going to see what would happen if you did have an infinite number of rectangles there. So how wide would each rectangle be if there was an infinite number of them? Well, they would be infinitely small, wouldn't they? They'd be approaching nothing. They'd have no width at all, almost. So we're going to consider this curve, and we're going to write some stuff down here and see if we can understand this. It's not the easiest thing to understand. So let's draw some rectangles again. I'll do them right bound like I did before. So one rectangle I could do would be, I'll do them a little bit thinner. I'm not going to do them infinitely small in terms of width, but I'll do them like that. I could do one like that, and I'm going to do them right bound again. It doesn't matter if I did left or right, but I'll just do right bound. So here'd be another one, and I think I'll just write, well, oh, I should have put this all the way down, shouldn't I? They're supposed to be the same width. I apologize. I'll do one more. So again, it's supposed to be the same width, right bound, coming down to here. And then I'm actually just going to write etc., because we would keep doing the same thing. And we would finish, of course, with one that's supposed to be the same width. It's right bound, just like all the other ones, like this. Okay? Oh, I guess I should put this down as well. Okay, you can see the starting point is A and the finishing point is B, and we want to know what's the area between A and B. One way we could do it is get the area of all the rectangles, including the ones I haven't drawn, and we could add them all up. We're naming our function y equals f of x. That's the blue function, right? We're getting the area underneath from A to B. Okay, a few things to talk about. First of all, this width, whether I look at the first one, second one, third one, I'll just do it up here on the third one. This width from here to here, we already have a name for that, don't we? We already have a formula for that. That width we call change in x. That's our width. And do you remember the formula? We've talked about it a few times before. It's b minus a divided by n. Okay, that's easy enough to understand. The next thing, I want to look at each of these points. So this point here is called A. This point here I'm going to call x1. I'm actually going to write it down here because we're going to write something else above it. This is x1. This point here is x2. This point here is x3. Then it would continue on x4, x5, etc., etc. And this one here would be point B, but we could also call it xn, because that's going to equal the number of rectangles, right? If we only have one rectangle, it'd be x1. If we had two rectangles, x2. If we had three rectangles, x3 would be the last one. But if we have n rectangles, the last one would be xn. But we could also call it b. Okay, now there's another way we could also represent these points here. Basically, to get this point, you're taking A, and you're having to add a certain amount to it to get up to here. How much do you add? You add this amount. You add change in x. This is getting very hard for me to write in here, isn't it? Alright, to get this point, what would you do? Well, you'd go A plus change of x plus another change of x, another width. So in other words, you're going A plus two widths. A plus 2 change in x. That's this one. How about this one? You would go a plus 3 widths, or 3 changes in x. And so what could you say for the last one? You could say a plus n number of widths, n change in x. Okay, hopefully that makes sense. That's how we're getting to all these points. We're starting at a. If we add one width, we get to here. If we get another width, we get to there. If we get another width, we add to there, etc., etc. Okay, I think that's everything we have to put on our diagram. Now let's write down some math and see if this makes sense. In order to get the area, what that's going to be approximately equal to, not exactly, but approximately, is you need to get the area of the first rectangle. Well, how much is that? Well, every width of the rectangle, for every single one of them, the width is change of x. So you would multiply change of x times however high it is. Well, the height is right here, and that's however much the function is equal to at x1, right? That's the height, is wherever this function ends up at x1. So you'd need to multiply by f of x1. That would be the first rectangle, plus the second rectangle. Well, the width is always the same, and this time though you'd multiply by however high the function is at x2, right there. F of x2 takes you up to there, and that's the top of the rectangle. So f of x2, and you can probably see what's going to happen. We're going to keep going. For the third one, it'd be the width times f of x3 plus ... We keep going and going and going, and then our last one would be this rectangle here, still has the same width, but now we would not want to know what f of, we want to know that point right there, well that's f of xn. There you go. If you were to do that, you would get an approximate area. But wait a minute, look at all these additions. We're adding, we're adding, we're adding, we're adding. Hey, you know what this suggests we might want to do right now? Why don't we use our new talent from last video of summations and use some sigma notation? So what's common in every single one of these things? Change of x, change of x, change of x, change of x. Oh, so obviously you're going to have a change of x. I'm actually going to put it at the end. I'm sorry. You're going to multiply by change of x. And you've also got, in each case, f of something, f of something, f of something. So you've got an f of x of, well now how are we going to do this? It starts off at 1, then it goes 2, then it goes 3, then it goes, hey, wait a minute. It starts off at 1, and then it goes all the way up to n. And if we put a little k right there, we've got it. We've expressed the top formula with sigma notation. Now, what kind of number do we want n to be? Do we want it to be small or big? Remember, n's the number of rectangles. We want n to be huge. We want n, the number of rectangles, to increase without bound. In other words, we want, therefore I'll put, or in other words, we want n to approach infinity. If you want, you can even put positive infinity, because we certainly don't want it to be negative infinity. We want it to be a massive number. We want as many rectangles as possible. So I'm hoping that kind of makes sense to you. You can follow along with my thinking here. If not, you're still going to be able to answer the questions, but it's always nice when you understand, right? So if f is continuous on the interval AB, we've talked about continuous, it means there's no breaks or anything, right? You can put your pen down and write from one side to the other. Yes, I can draw that whole function without lifting my pen, so it's continuous. On the interval A to B, right, it went from A to B, which is what we're interested in. And we divide it into n subintervals of equal length. We divide it into n rectangles, basically, of equal width. The area under the curve over that interval is defined by the following. And then what I have here is exactly what I just wrote up here, except for one thing. We've added in this limit part. We want n to approach infinity. So we want to know what's the limit as n approaches infinity. Now, a couple things. The width, which is change of x, we already know this. Width is equal to b minus a over n. And xk, that equals a plus k times change of x. Why is that? Well, that was this bit, right? Remember this part in blue I talked about? We're starting at a, and we're adding one width, and then another width, 2 widths, and then 3 widths, and then all that. That's basically what this is saying right here. It's telling you to get to each one of the points down here. You're going to start at A and add a certain number of widths to get to each one of those points. All right, we are going to use this fact, this formula, to solve this question, and we're going to get the exact answer this time. So, find the area of the region bounded by y equals 16 minus x squared and the x-axis on the interval 1 to 3. So we don't have to do this, but let's actually sketch this. Why not, right? Now we're only going from 1 to 3, so I can just draw in the first quadrant. And 1, 2, 3. Now you should know what this looks like. This is a parabola that's facing downward and has its vertex at 0, 16. I'll even start at 0. So we're going to go up as high as 16. So let's just do it like this. 4, 8, 12, 16. And I know we're only going from 1 to 3, but actually, let's just go 0 to 4. It's easy to graph. So if you put 0 in here, 0 squared is 0, 16 minus 0 is 16. If you put 1 in here, 1 squared is 1, 16 minus 1 is 15, so you're almost right at the same spot. If you put 2 in here, 2 squared is 4, 16 minus 4 is 12, so you're about here. Put 3 in here, 3 squared is 9, 16 minus 9 is 7, so about there. And if you put 4 in there, 4 squared is 16, 16 minus 16 is 0. So this is supposed to be, I know it's not the greatest drawing, but it's supposed to be half a parabola, right? And what we're interested in is how much area is bounded from 1 to 3. How much area is there underneath the curve but above the x-axis? We're going to find this area right here. Okay, so let's start. One thing we want to know is we want to know the width, the change in x, which we know is b minus a over n. So let's plug in what we know. Our b is the second number here, it's 3. Our a is the first number here, it's 1. Our n is the number of rectangles. Wait a minute, we don't know how many. We want as many rectangles as possible. What? Well, I don't know what to do. We'll just put n. We can't put a number in there, we'll just keep it as n. 3 minus 1 is 2, and we still have n there. Okay, that's it for that. Now, another part of the formula, if you look back, was xk. And we said that that was equal to, remember that's like each successive point, that was equal to a, your starting number, plus a successive number of widths. So let's see what happens. Where are we starting here? We're starting at 1, right? Our a value is 1, plus k, well, I don't know what k is, but I do know what the change of x is. We just figured it out right here. X is 2 divided by n. So we can simplify this a little bit. We still have the 1, but now if I multiply here, I get k2, or 2k, over n. Okay, so these are two very important pieces of the formula. So let me write the whole formula down now. Okay, here we go. I've written out the formula. It doesn't look that long, but we got a lot of steps to go. So I'm not going to write area each time, I'll just put equals. I guess I do have to write, I mean I understand if you skip this as you're working through these epically long questions, but I'll write it. So k equals 1, and there's nothing, we don't know what n is, so far there's nothing different. Now we get to the part we can do some stuff. So what we're going to do is find out what is f of xk. Remember, we have xk, it's right here. So what does it mean, f of xk? That means take xk, which is this, and put it into the function. Put it into here, right here. Well, specifically, put it into the x. You got to put it in right there. So what we end up with is, I'll put it in brackets, 16 minus, now I've got to put the highlighted bit into the x. So I'll do another bracket, 1 plus 2k over n squared, right? It's 16 minus x squared, and we're putting the highlighted part into the x, so you get 16 minus all this squared. So I'm going to turn this into a square bracket. I think it might be easier to understand what's going on here. So that's our first bit. All we've done so far is this. We still have to do this, change of x. What should we write for that? Well, look, right up here, change of x is equal to 2 divided by n. So that is what we're going to write here. And now we do a lot of simplifying. So I'm going to write the first part again. So I have 16 minus, now I got to square this. If that's hard to do in your head, you might want to write that out twice, right? We're doing 1 plus 2k over n multiplied by another 1 plus 2k over n, and then we're doing our mountains and our valleys. We're doing it all. So what do we get? 1 times 1 is 1. 1 times 2k over n is 2k over n. 2k over n times 1 is another 2k over n. 2k over n times another 2k over n is 4k squared over n squared. And then we still have the 2 over n here. Alright, let's keep going. So let's do a couple things here. We can do 16 minus 1, which is 15. Now remember, this minus refers to everything. So when we combine 2k over n and 2k over n, the denominator stays the same, and 2k plus 2k is 4k. But remember, this is actually minus that amount, so it's going to be minus 4k over n. And same here, you have to minus this, so it's minus 4k squared over n squared. And we're multiplying by 2 over n. Okay, let's actually multiply now. So we have to multiply this 3 times. See what we get. So 15 times 2 over n is 30 over n. Minus 4k over n times 2, you get 8k over n squared. And multiply these, you're going to get 8k squared over n cubed. Okay, next thing we should do, see where we have 3 different pieces here, 3 different terms. Let's remember when we have that and we're doing sigma notation, we can apply the sigma notation to each piece. That's what we're going to do here. So you're going to write the sigma sign exactly the same and just apply it to the first one, minus the same sigma notation with the second one, and then the same sigma notation with the third one. And then you'll need to put all this in brackets to show that the limit refers to all of this. Okay, ridiculous how many steps this is, right? Okay, now in each one, remember if we have a constant, we can move it in front of the sigma notation. So 30 is definitely a constant, and actually the n's are constants as well. So you can move both those things in front of the sigma sign. And then the only thing left here would be, well, 1. Minus, let's do the same thing. You can move the 8 and you can move the n squared. And so then what's going to be left, oh, this is so messy, is just k. And same here, you can move the 8, the n cubed, and what will be left is k squared. Gosh, my sigma signs are ugly. Okay, the next thing, you're going to have to look at those formulas we talked about in the last lesson. Do you remember what happens when you just have a constant? In this case, the constant's 1. You just multiply that constant by n. So this sigma part here just equals n. You end up with 30 over n times n minus. All right, we've got our constant up front. Do you remember what happens when you had just a k here? It ended up you would get n times n plus 1 over 2. Remember, these were just some formulas that I gave you in the last video. You can check that out if you want. And then for the third one, we have our constant amount. What happened when we did the sum and it was k squared here? It equaled n times n plus 1 times 2n plus 1 all over 6. Alright, the next step's great. Cancel. Cancel this n with one of them here. You certainly cannot cancel that n with that. Can't cancel a binomial unless there's another binomial. You can cancel this n with 1 here, so now you're down to 2 here. You could also cancel this 2 and this 8. You have 4. This 6 and this 8. you have 4 and 3. Alright, hopefully that's not too messy and you can understand what I'm doing. So this first term, all you have left is 30. The second one, you have 4, you have an n plus 1, and you have an n. The third one, you have a 4 and a 3. You'll have an n squared as well on the bottom, and then on the top you still have an n plus 1 and a 2n plus 1. Okay, we're going to need to expand here. We multiply on the top, you get 4n plus 4 over n, and you multiply here. Alright, let's think of this. This is 4n plus 4 times this, right? So it's 4n times 2n, which is 8n squared. It's 4n times 4, which is 4n, and 4 times 2n, which is 8n, so you get 12n. If you want, write that all out and multiply it, but I gotta get going here. This is taking too long. And then for the last term, you have 4 times 1, which is 4, times another one, so it's plus 4. And that's all over 3n squared. Okay, a good strategy now is let's put each one of these things, like since this is 4n plus 4 over n, that's the same as 4n over n and 4 over n. Well, wait a minute, 4n over n is just the same as 4. Now remember, this minus also refers to this, so minus 4 over n, we can't do anything. Minus 8n squared over 3n squared. Well, the n squareds would cancel. You would just have 8 over 3. Okay, minus, this minus refers to this, so you have minus 12n over 3n squared. Well, the 12 and 3, you get 4 on top, and then you have 1 extra n on the bottom. Minus also refers to this, so another minus, and there's actually nothing you can do. Okay, we can finally stop writing this statement, the limit. We're actually going to take the limit here. So, what happens? Well, we have 30, we have minus 4. Now, do you remember what happens when you take the limit and you have 4 over infinity, or any constant over infinity? So this is 4 divided by a massive amount. What's it approaching? Well, you're breaking it into so many pieces, you're actually approaching nothing. You're approaching 0. Minus 8/3. Look, you got exactly the same thing here. It's a massive number on the bottom, so it's going to be approaching 0. Minus, same thing here, right? You take a massive number and square it, it's even more massive. Multiplied by 3, it's even more massive. So 4 divided by that big of a massive number, it's approaching 0. So basically, all you have to do is 30 minus 4, which is 26, and take away another 8/3, and you'll have your answer. Should we get common denominators? Why not? Multiply top and bottom by 3, and you'll get 78 over 3 minus 8 over 3 for a final answer of 70 over 3. And this is, my friends, exactly the area under that curve right there. Exactly. Now, look at all those steps. Oh my goodness, must be one of the longest questions you've ever done. Talk to you soon. Bye.